It's time for our third and final application of work, which is pumping problems, aka fluid lifting problems. So you're going to lift, but you're lifting fluid. You're lifting water instead of lifting just a chain or a rope or an anchor or something like that. So let's look at how we do these. What we'll do is we'll draw a y-axis in the vertical direction, of course parallel to gravity because gravity pulls downward. And we're going to choose a convenient origin. Usually it's at the bottom of the tank, down here, or at the top of the tank up here. It's one of those two. And then for, assume the interval a is less than or equal to b, or from a is less than or equal to y, which is less than or equal to b, corresponds to the vertical extent of the fluid. And then you have a cross-sectional area of the horizontal slices and the distance that the slices must be lifted. So you're taking fluid, here, give me 1 second. For example, the iced tea in my cup. And you can see that I have iced tea in this cup, and then you imagine the bottom is at the origin and you cross section into it and cut into it, and it would form circles. And so you find the area of those horizontal slices, in this case of this cup it would be circles, and then you lift them from wherever they are in the cup up. So the work would be, let's see, so we have gravitational constant, so, or excuse me, that's gravitational constant. This is rho. Rho is density, which is usually in kilograms, let's say per meters cubed. That's a pretty common one. It can sometimes be grams per centimeters cubed as well. It's right down there for water. For water, it's always that. Now, if it's a different fluid or a different liquid, it would have a different density. But water is this. Okay, so then, well, the volume is a V, right? And its mass, it would be rho V. Rho is the density of water. All right, so then G is gravity. I mean, that's pretty obvious. So G is the gravitational constant. No problems there. That's usually in meters per second squared. And then area, well, if we're going to be doing meters, that means that we would want area of a cross section. So if you cut across your cup of tea, right, you hack across it. So it's the area of a cross section. So cross section area, which is A of y, which would be in meters squared because it's area, right? And then we would multiply it by d of y, which is the distance that we have to lift it. D of y is distance, and distance would be in meters. And then, of course, dy is the thickness of the wedge of water you're trying to lift. So dy is thickness, which is also in meters. So if we look down here, right, dy is right here, right? It's the thickness of the wedge you're trying to lift, right? A of y is the cross section. So A of y is this cross section right here, right? The area of the cross section, I should say. D of y is the distance you have to lift it, right? And it's a function of y because you're lifting vertically, right? And then gravity and density just have to do with, well, gravity is gravity, and density has to do with the liquid inside. And again, if it's water, it would be 1 gram per centimeter cubed or 1,000 kilograms per meters cubed. Now, if you'll notice what happens with all of this, meters cubed down here, and then meters and meters squared right here. So meters cubed, meters, meters, meters will leave me kilograms, meters squared, and seconds squared. Kilograms times meters over seconds squared is Newton meters, which is joules. Right? Okay, so notice that water from different levels of the pool is lifted different distances. So you actually, it takes more work to lift water from the bottom of the pool than it does from the top of the pool because it's not going as far, right, at the top of the pool than it is at the bottom. And then equal of water from the same depth requires equal, so it must have been equal amounts, sorry about that, equal amounts of water from the same depth require equal amounts of work to lift. So it doesn't matter if you're lifting it from over here or over here. It's coming from the same area and the same depth. So as long as it's the equal amount, like take a cube over here and a cube over here, it's going to be the same amount of work to lift it out, as long as it's from the same depth. And then again, it's just handy to know, for water, this is rho. And again, you can do a little bit more with water. I mean, you can get heavy water that has extra hydrogen items and stuff like that, but we're not going to deal with that. So for our purposes, we're just going to say water is has one of those two as its density constant. Okay, so let's actually put this into practice, because these problems can be a bit tricky. So we have a simple swimming pool, and it's got a depth. Oh, it's a large rectangular box. This is a very simple swimming pool. So we're going to draw a very large rectangular box. Okay, and then over here, I'm going to have its side. It's going to go like that. Now we are going to pump water out of this pool. Anybody who owns a pool know that you actually do have pumps, that this is a thing that you need to have with pools. So they actually do need to be able to pump water out. Now we are going to pump water out of this pool. Let's see, it's a large swimming pool, shape of a rectangular box with a base that measures 25 meters, which I've obviously made this side because it's very long, by 15 meters over here on this side. So there's the base, 25 meters by 15 meters. I mean, if you want, there's the rest of the pool if you want to see it. Okay, so we are going to, at a uniform depth of 2.5 meters. So that means that I know that this distance right here is 2.5 meters. Oh, I didn't leave myself enough space for the M there. So 2.5 meters from here to here. And then I know this is 15 from here to here, and then this is 25 from here to here. Okay, so then I've done all of that. 25 by 15, 2.5, done. Now, how much work is required to pump out the water a level to, there's a typo there, to pump out the water that is 0.2 meter, or to a level, sorry. Pump out the water to a level, sorry about that, that is 0.2 meters higher than the top when it is 80% full. Ooh, okay. There's a lot of stuff going on there. All right, so let's think about this. So the pool is 80% full. So I'm going to kind of draw the water in here. Actually, that water you can see. All right, so there's the pool, and it's 80% full. All right, so we just got to think about that. So from here to here is 80% full. Okay, so the pool is 80% full. And then we want to know how much work is required to pump the water to a level that is 0.2 meters higher. That's this bit right here. So from here to here is 0.2 meters. I did it on purpose. I made the pump come out up higher than the pool actually was. Now the pool is 2.5 meters. Actually, that's a better place for me to put that, 2.5 meters. I'm going to do that, because I'm going to need the left side over here to do other things. All right, so that's 80% full. I know that this distance right here is 2.5, all the way to the bottom to the top of the pool. And then I know I want to pump the water even further. I want to pump it 0.2 meters above. Okay, so now let's imagine a wedge of water in there. If I imagine a wedge of water, like I cross section into this pool, and I get a thin slice of water. That slice, first of all, would have a thickness of dy, right? So this has a thickness of dy. Okay. All right, what else? So it has a thickness of dy, and I want to pump it out. Now it's at a height, I guess this is a question. Where do we want to put the origin? I think it would be smart to put the origin right there. Right? Let's say, well, I don't really need to know, its coordinates. What I need to know is that this is y equals 0. So I'm going to do that. So I'm going to say the bottom of the pool right here is y equals 0. Because that would just be smart. We'll make the bottom of the pool 0. Otherwise, you have to deal with negative numbers, and nobody wants any part of that. So if I say that this little wedge of water is at y height, then it has to go how far out? What's the distance the water must travel? That's d of y. All right, so let's put this together just a little bit. All right, so work is equal to the integral from a to b rho g a of y d of y dy. Okay. All right, so equals the integral. I know almost none of this. I do know that it's water. Because it's water, I know that rho, and everything in here is meters. So I know that that must be 1,000 for rho. And gravity, I also know, because gravity is gravity. Gravity is 9.8 meters per second squared. So those two I've got. And keep in mind, by the way, this is kilograms per meters cubed, and then this was meters per second squared. That's what I'm using. All right, now I need the area of a cross section. Well, if you look at this cross section, when I cut into that pool at that height, it makes a rectangle, right? So the area would be equal to a rectangle. No, I was right. A rectangle, which is 25 times 15. It's actually constant. No matter where I was, low or high in this pool, it's 25 times 15. It's a rectangle when you hack into it crosswise. And then d of y. Well, that's the tricky part. Because d of y is the height or depth which I want to raise this water to. So if the water is at y height, d of y is, well, let's say, if this is y, what's this total height here? It's 2.7 because it's 2.5 plus the 0.2. So this is 2.7 take away y. Like that. Because you have to raise it. See, if it's at y, you got to raise it 2.7. Now, if you were just going to the top of the pool, it'd be 2.5. But you're actually trying to go 2.2 meters higher than the top of the pool. So that's 2.7. Now notice that the units for these should all work out. This is meters, and this is meters. So it should work out to be meters times kilograms. And then, of course, we have a dy at the end. dy is also in meters. So it should work out that it's kilograms times meters squared divided by seconds squared. So that way we'll have our work in joules, which we will. So that's great. So I just checked all my units as I went. All right, now A and B. Well, A will be the low part of the pool, right? Because we're going to raise this water from 0 to where? Here, let me do it in blue. Well, it's 80% full. This is where the 80% comes in. Because if it's 80% full, then I need to know what 0.80 times 2.5 is, because that would be 80% full, which would be 2, right? It's 4/5. 4/5 of 2.5 is 2. So 2 meters. So the water is at 2 meters. So I'm going to go to 2 right here. And you want to make a little note. It's because it's 80% full. If it was full, you'd go 2.5, right? Because you'd end up at 2.5 for the end of the pool. So this part comes from the fact that you're going 0.2 meters higher than the pool. That's why it's 0.2 or 2.7. And over here it's 2 because that's where the water ends. All right, once we're here, this isn't so bad. I just need to find out what these numbers are. So let me grab Desmos. There. 1,000 times 9.8 times 25 times 15 is 3,675,000. All right, so all of that stuff becomes a constant out in front. So these two pieces all go out in front. So it becomes 3,675,000. And then we integrate what's left. So then the integral from 0 to 2 of 2.7 minus y dy. Oh, sorry, I should have done those in that different color blue. Okay, so then that's a really easy integral to do because this is 3,675,000, and that would be 2.7y minus 1/2 y squared from 0 to 2. All right. So obviously the 0 is not relevant because 0 would just be 0 in there. What is relevant is the 2. So it's 3,675,000. And then it's 2.7 times 2 minus 1/2 times 2 squared. This is what Desmos is for. So let me go grab it. Okay, so 3 million. Well, actually, let's just do 2.7 times 2 minus 2. So that's 3.4. And then 3.4 times 3,675,000 is 12,495,000 Newton meters. Now remember, it has to be Newton meters because we already figured out the units when we did the integral. So it's kilograms. The meters cubed here cancels with the meters squared here and then the meters over here. So you end up with it's kilograms times meters squared over seconds squared, which is Newton meters, which is joules. So we can just that. Capital J for joules, and we'll just leave this as a note.